Deliveries. Isn't it wonderful to order something and have it brought right at your door? But there's a catch. We have to pay for this convenience, right? Well, if we ask someone to bring something to us, we are not paying just for the item itself, but also for the journey it takes through traffic, rain, and whatever nature throws in their way. So if I live in Haifa, for example, and I want to order something from Tel Aviv, the delivery fee will be high, right? Some of us might even reconsider our purchase when we see the delivery cost. But there is another type of delivery that is fundamental to our daily lives, yet many of us don't even realize it. I'm talking about electricity. Think about it. Have you ever wondered about the journey electricity takes before it powers our homes? Once sent, electricity is going through wires that has resistance, which means that some of the energy is lost as wasted heat. This is called electric resistivity. Do you know that there is a state of matter where energy can flow effortlessly? Once sent, it can continue flowing wherever we want with no extra cost. Just like an astronaut in space, that if he jumps and he won't have a rope pulling him back, he can continue floating forever. This magical phase of matter is called superconductivity. So by using superconductivity, we have the opportunity to make energy system much more efficient. Superconductivity offers even more incredible possibilities. Here you can see magnetic levitation. When a superconductor is placed above a magnet, there is some rejection force, similar to when you try to bring together two magnets of the same type, but they reject each other. And here, what you see is that because of this rejection, the magnet or the superconductor is levitating above the other. So if you have this wonderful phase of matter that can do a lot of great things, well, where's the problem? This superconductivity occurs only at extremely low temperatures. To use this, we have to cool these materials down to hundreds of degrees below freezing, which means it will be very hard technologically and also very expensive. But in 1986, there was a groundbreaking discovery. Materials that exhibit superconductivity at temperature had never seen before. They are called high-temperature superconductors. And they operate in temperature far above the condition required until then. So when I'm saying high temperature, I don't really mean high. It's much colder than the room temperature we are all in right now. But this is significantly higher and much more accessible. From that, many practical applications have emerged. And in this photo, you can see the Japanese maglev train, which floats above its track, which means that if you remember the levitating magnet from the lab, now it can get out of the lab and be used in practical applications. Other practical applications like medical imaging and quantum computing have also emerged. So everything sounds great. What's the catch? Well, the exact mechanism behind this high-temperature superconductor is yet not completely understood. It remains a mystery. So that's where my research comes in. These superconductors are studied all around the world in different approaches. I focus on high-temperature superconductors, specifically ones that come with magnetism. Why magnetism? Well, every material is made up of electrons, which are tiny particles responsible for carrying the electricity. So each electron can point in a different direction. Let's mark it with an arrow. Now, if I'm looking on classical magnetization, all of these electrons will point in the same direction. However, in conventional superconductivity, the electron will pair up and be in opposite directions. So if I'm looking of a state that is both magnetic and superconducting, how can these electrons be in the same directions and opposite directions at the same time? That's what I'm studying. I'm trying to understand whether these two phases are sitting next to each other or they are somehow combined. If they are working together, then how exactly is it working? It can be really interesting. But if they ruin each other, then how do they coexist? So to study that, I need to look on a very small scale, very minor changes. For that, we are using in our lab an extremely sensitive magnetic imaging device known as scanning SQUID. You can think of it as a handmade microscope where instead of visualizing small objects, you see magnetic properties. By this technology, we are able to see tiny amounts of magnetic properties. We can look on states, how they emerge, how they evolve. And we have a local view, which is critical to see how these states start, how they interact, and examine this combination. Under this microscope, I'm placing interesting materials that are made by taking different materials with different properties, and these layers are stacked one above the other, creating new material with new properties. Specifically, I'm interested in a group called Kagome structure crystal, which has triangular symmetry that can lead to very unique and interesting properties. So how do I do that? Let's look at an example. I'm taking some sample and I'm putting it inside my handmade microscope and cooling them all down. Now I scan this sample and I get different maps of magnetic responses. For example, here you can see the magnetic response and the superconducting response. These two images are taken at the exact same time, exact same place, same conditions all the time. So now I can compare. For example, if I have some black lines here that are low superconductivity, how will it look on the magnetic map? Then I can change the environment, move different parameters like temperature or electron density, and see how these states evolve and compare how each one works and how do they interact. So by using this local view and high accuracy, I can compare these magnetism and superconducting maps and investigate it. So by exploring these unique materials, I'm aiming to add another piece to the puzzle of unconventional superconductivity. This way, we can pave the way for new breakthroughs in both fundamental science and practical applications. Thank you.